Hi, my name is Katie Klinging-Smith, and this is Advanced Concept Presentation 2, where we will be deriving the Michaelis-Menten Equation. So this is essentially describing the kinetics of enzymes as they react with substrate, which in this equation is represented by S. So these first two steps are written out for us already. Reaction 1 proceeds both forwards and backwards, represented here by K1 and K negative 1, resulting in enzyme substrate. So this is E and S. This is combined into the enzyme substrate complex, or the Michaelis complex is also called that. This reacts into an enzyme and a product. So this product that's created isn't enough to also create the backward reaction here. So we just have K2. If it were creating a backward reaction, it would probably have like a K negative 2 here, but since it's not, we have just K2. All right, so step 2. This is step 2 here as it comes through. So this is step 2 with just K2 is only forward reaction. So essentially S to P is the net reaction here, substrate to product. All right, so the second step here is written out already. This is where we have K1 times E times S minus K negative 1 times ES minus K2 and ES. So this is written out in a way that gives us 0 in this equation. So here, when everything equals 0 here, we're able to, so it's basically reaction K1 minus K negative 1 consumes ES. K2 also consumes ES, and it all equals to 0. So the problem is here, we need to solve for the unbounded enzyme E. That's E sub T, which represents the total concentration of enzyme. When you subtract ES from both sides, you can solve for E and sub E into this previous equation. All right, so once we solve for E here, we have the unbound and the bound, so we're going to plug that E back in. So once this is distributed into the previous equation, so step 3, we want to distribute and solve for the concentration of ES. So now we want to move ES to the left side of the equation. So this brings us to these next steps. So what we want to do is distribute ES and get 0 on that one side, and that's going to continue here as we distribute out the K times ET times S minus K1 ES times S minus K1 times ES minus K2 times ES. So we still need to isolate to solve for ES here. So in order to do this, we're going to have ES times K1 times S plus K negative 1 plus K2, and that's going to equal what we have left over here from the distribution, K1 ET times S. So we still need to get ES by itself here. So what we want to do is take this side of the equation, divide it over here. So that gives us ES equals K1 times ET times S. Make sure that's still in focus. Good. All right, so, and then that's going to be divided by K1 times S plus K1 plus K2. And to kind of condense this down, we multiply by 1 over K1 divided by 1 over K1, and that gives us ES equals ET plus substrate S divided by substrate S plus K negative 1 plus K2 over 1. All right, so after we have all this, we get, all right, step 4 here I have labeled. So what happens here is the instantaneous rate of change for product P is a function of its reactants. So for K2, there's only one reactant, and that's ES. So we know that the instantaneous rate for product P is K2 times concentration ES. So in the previous steps that I was just showing, we already solved and have the equation for ES. And this is where we substitute the equation for ES into this equation, and then we get the Michaelis-Menten equation, at least in a less condensed form here. So we get a V velocity equals dP over dt equals kcat. Kcat is essentially just K2, same thing, so the turnover number, times ET times substrate divided by substrate plus Km. All right, so the turnover number here, kcat, is the maximum number of molecules of substrate S that an enzyme can convert to product per catalytic site per unit of time. Or in other words, how many enzymes a molecule can work with per second. So given that it's how many enzymes a molecule can work with per second, that's essentially the max rate, or Vmax. So this up here, this numerator, this is actually the maximum rate, which is what we've been calling Vmax. So this is actually Vmax right here. All right, so as ES goes up, so does the rate of reaction. And that is demonstrated here. V equals Vmax times S plus Km. So how much substrate can an enzyme catalyze is essentially explained here. We have Vmax times substrate S divided by 2 times substrate S, and if we condense this down, we see that the S's just cancel here. Yep, the S's just cancel here, and we have Vmax divided by 2. So what that means is this can actually tell us a lot about the Michaelis constant Km. So in the denominator we have Km. This is concentration of substrate at which the reaction rate is equal to half the max velocity. Km also tells us about affinity for enzymes. So in this case, shown in this proportion here, if Km is low, it has a high affinity. If Km is high, it has a low affinity. So Km here is represented in the Michaelis-Menten, now I can't even say the title, the Michaelis-Menten, find it, Michaelis-Menten equation here. So written out in its condensed form, Vmax, which we talked about up at the top here, which was essentially this kcat or K2 times ET times substrate S divided by substrate S plus Km. So condensed down, we just described what Vmax was. So we have Vmax times substrate S divided by substrate S plus Km. So this is our final equation here. And another thing, I think I mentioned it, as ES goes up, so does the rate of reaction, which would be shown with that here. Yeah, I think I covered everything. This is the third time I had to film it because initially my phone overheated, and that's why it's already written out. So I rode through it a couple times already, but here we go. And thank you for listening.